Okay, so in this video we're going to look at some slightly more challenging shapes of molecules where we've got incomplete octets, expanded octets, double bonds and charged molecules. So for the first example here, beryllium chloride, we're going to start as we normally do, where we put the beryllium in the center here because it's the one that we have the fewest of. And our beryllium has 2 valence electrons. Okay, 1, 2. If we look at chlorine, we have, sorry, in a different colour there. If you look at chlorine, we have 7 valence electrons. And we have 2 of those, so times 2 makes 14 electrons total there. 1, 2, 3, 4, 5, 6, 7. Okay, so we're going to put the chlorine either side. Now, because beryllium only has 2 electrons, it's only able to bond twice, because to make a bond it has to share an electron with the chlorine there. And so chlorine will share back, and that forms 2 single bonds either side. Not forgetting chlorine's electrons there as well. Now, if we look at the beryllium here, we've got 2 bonding pairs, which means we only have one option for the shape of this molecule, and that's what we call a linear molecule, where if I draw it, it simply looks like that, with 180 degrees because of the repulsion between the 2 bonds. For the next one, we're going to look at sulfur hexafluoride. So sulfur has, once again, we're going to count there, sulfur has 6 valence electrons. Okay, so 1, 2, 3, 4, 5, 6. And fluorine has 7. 1, 2, 3, 4, 5, 6, 7. And so that's times 6, which means we actually have 42 electrons there. So plus the 6 makes 48 that we should have. Now, when I draw this, I'm going to put sulfur in the middle because it's the one I have fewest of, and I'm going to put fluorines around the outside. Now, this is a 2-dimensional diagram, so I'm going to spread them out as a hexagon shape there. And sulfur has 6 electrons, so all 6 of those are going to be taken up in bonding. Because remember, a bond is a shared pair, so each of the sulfur's electrons has to be distributed around like that, and the fluorines will share back with one of their electrons. Now, that means that there is 12 electrons around the middle there, which is what we call an expanded octet. So that's going above the regular 8. This is possible for larger elements. If I just put the rest of the lone pairs on there to complete the diagram, and then what we're going to do is do the 3-dimensional diagram. So in this example, I have 6 bonding pairs. Okay, it's important to check the electrons, and I have the full number there of 48 electrons. I'm now going to look at my options for shapes. 6 bonding pairs with no lone pairs gives us the regular octahedron structure there. So that's the shape of the molecule. So we're going to get sulfur with everything bonded at 90 degrees from each other, forming an octahedral shape, which is the furthest apart each of the bonds can get. Next one, is carbon dioxide. So this is an example where we're going to have to use a double bond to complete the octets. So we'll start once again with carbon. Carbon has 4 valence electrons. Then we're going to look at oxygen, which has 6 valence electrons, and we have 2 of them, giving us 12. Okay, so adding them up, we should have 16 at the end. We'll just draw them around there. Okay, so what we're going to do first is we're going to put the carbon in the middle because it's the one that we have the fewest of. We're then going to put the oxygens around the outside. Now we're going to look at how many that each need to complete. So oxygen needs 2 more, carbon needs 4 more. So they are able to share, and they'll share twice to complete their octets. So this is where we draw it a little differently. So that's a shared pair, and that's a shared pair, as is that and that. And that forms what we call a double bond. Now, not forgetting the lone pairs that are on the outside here. This gives us a linear shape molecule. So if I was to draw this, it would have a double bond and a double bond with 180 degrees. Lastly, we're going to look at charged molecules. So here we've got NH4+. So unlike the ammonia, if we just go back and recap ammonia's NH3, we had 5 valence electrons and 1 valence electron on the hydrogen, meaning that around the outside we had 3 bonds forming, NH3, and a lone pair underneath. That lone pair gave rise to a tetrahedron with a lone pair at the top, which actually ends up being called pyramidal, and specifically trigonal pyramidal. We're going to look at NH4+, so slightly different. And with NH4, we start the same. So N has 5 valence electrons, and H has 1 valence electron, and we have 4 of them. But then we also have the charge, and the charge is minus 1 valence electron. So a total of, I'm just going to do total down there, a total of 5 plus 4 minus 1. The reason it's minus 1 obviously is because plus charge means it's lost an electron. So that gives us a total of 8 electrons around the molecule. So let's have a look now, and we're going to draw the nitrogen in the center because it's the one that we have fewest of, and the most electronegative. Then we're going to put hydrogens around the outside. Now nitrogen has 5 electrons, so it's got 1, 2, 3, 4, and then this is why there's a positive charge. Actually, to form this substance, the hydrogen has actually lost an electron and bonded straight to nitrogens. So nitrogen supplies both the electrons for that bond. And these ones are normal shared pairs. So this actually makes a total of, and I should add that there is a positive charge here overall. And this gives us 4 bonding pairs, which results again in a tetrahedral structure. So once again, this is positively charged, N in the middle, and hydrogens around the outside. So it's the same structure as methane. It's a regular tetrahedron. So that's how you do the slightly more complex examples.